So back again, now we're going to talk about some endothermic reactions besides the exothermic that I just talked about. So the good thing about endothermic is it's just the flip of exothermic. So remember, endothermic is going to be absorbing heat. Endothermic is absorbing heat. So I have this chemical reaction. Sodium bicarbonate, sodium hydrogen carbonate. Then I have the heat here, and then I have sodium carbonate, water, and CO2. Now again, I mentioned in the previous video, states of matter are going to be important because if you have different states of matter, you get a different amount of heat. Right now, it's not going to make that big of a difference, but it is important for a chemical reaction. So please note that the heat here in kilojoules is listed on the reactant side. So write down reactant side. That is going to indicate you have an endothermic process. Endothermic process means you have to put energy in order for you to make the product. So this one is sometimes a little easier to understand because I got to put heat in order for it to happen. So I have to have it on the reactant side. Another way you can see it, just like with exothermic, is you could see it as a delta H. Okay, now please, like I mentioned in the other video, this is exactly the same number. Okay, no difference here. And like in the previous video, this is going to always be a positive value when you write it in the equation. Whether this is an endothermic or an exothermic process, you are just going to put it either on the left or the right-hand side of the arrow. In the second way of writing an endothermic process, delta H is going to be listed as 129. Now, of course, we don't write positives, okay? We don't write positives for our numbers, but we can say, since there is no negative there, that it is a positive 129. If it's a positive 129, that is an endothermic process. And so an endothermic process is always the delta H is going to be positive, always going to be positive. So exactly the same reaction, I've just taken the heat out of the reactant side. So the third way, like I said in the other video with the exothermic, is you could do a graph. Okay, now this graph makes a little bit more sense than the exothermic graph, just by understanding where the reactants and the products are starting. So draw yourself a very simple graph, and again, this is going to be reaction progress. You could even call this time. At this point in time, I don't care if you call it time, because again, that's really what we're looking at is the beginning and the end of the process. So this is a reactant going to product there. This is heat over here on the y-axis, or you could call it H. So using this as my example, okay, I have to put heat in order to make product. So how you're always going to see the graph is reactants are always going to be lower than the products on this graph in terms of energy. So I have to put energy in to make the product. So my reactant here is just sodium hydrogen carbonate. And then my products are Na2CO3, sodium carbonate, water, and CO2. So the difference between where the reactants are starting in terms of energy level or heat level, if you want to call it that, to the products, this is your delta H. And this is a positive value because this is an endothermic process. So this one makes a lot more sense. I got to put energy in order to make this product. If I don't put this energy in, it will not make product. So the reactants are at a lower energy state than the products are. So endothermics in chemistry are usually not common in terms of going to product unless you actually put heat in. So you have to put it on a hot plate, you have to put it over a Bunsen burner or something like that in order for you to make product. Okay, so again, these are the three ways you could write a thermochemical equation: heat in the equation, a delta H on the side, or a graph. And you're going to have to know all three ways of writing a thermochemical equation: exothermic and endothermic.